Greetings everyone. Uh, we waited till 3 and today uh, I am having some problem with electricity. There is no electricity currently, so I will turn off my video so that the battery performance of my laptop is maximized, and we will start the session. uh, since some of you have joined, let's start the session, which is our seventh live session. And today we will be solving the problems of the related to the PN junction. Previously we had solved one or two problems regarding this PN junction, but today we will deal further into this PN junction problems. Okay, so in this figure over here you can see that there is one uh, diode, which is basically a PN junction. So a diode, it basically, you have seen that how it works, that we have P side and we have N side. That is one side, or one kind of doping on one side of the material and another kind of doping on the other side of material. If I am considering homo material, let's be careful regarding the definition. First, we have said that the material is homo kind of a thing. It's not a hetero material, because hetero material are can be used for the diode, you can say, or PN junction functionings as well. But in here, for the basic cases, we start with the homo junctions. That is, on the P side and on the N side, we are having the same material. That is, we will be having same electron affinity for the P side and the N side. You will see when going further into the in depth of these device physics, you will see that there can be P material. P material will be of, let's say, of P kind of a material will be silicon, and let's say N kind of a material will be from germanium. So that would make it kind of a silicon germanium PN junction. Okay, you can have hetero junction as well, but as of now we are dealing with these homo PN junctions. So let's consider this diode, and it is given that this diode, which is basically, wait a second, there is some issue with the pencil. What is happening with this? Oh, it's showing that it is not charged. So basically, let's discuss till then. I think it will take about 2 to 4 minutes to get charged. So what I was saying that if I am having P kind of a material, you must have heard that there are different kind of heterostructures. Like, for example, we will be having a band, for example, where this P material will be having a much larger band gap, and this N material will be having smaller band gap, and this N material will be between the conduction and the valence band of the what we can say conduction and valence band of the P material, as a result of which we will be having one type 1 kind of a heterostructure. So there are different types of heterostructures when we deal with these what we can say junction kind of things. So basically over here we just deal with the homo junction. We say that we are having P or what we can say P and N are of the same material, as a result of which the doping is the main factor. And also, whenever we see this electric displacement relation, from that relation we would say that the electric field at the junction on the left side would be equal to the electric field on the right side. So it's just at, for example, if we consider the junction boundary to be at x equal to 0, we would say at x equal to 0 means electric field on the P side will be equal to the electric field at x equal to 0 plus. So this is some small what we can say assumption, or small you can say uh, liberty that we get in case of the homojunction materials, while in case of the heterojunction materials electric displacement has to be equal. Okay, so it has to be epsilon naught 1 times the electric field 1 equal to epsilon naught 2 times the electric field 2. Let me check whether the pencil has got charged a bit. Yes, it has got charged a bit. Wait a second, let me check again. Okay, it's 17%. So let's make it about 30 to 40% so that we can get started. Oh, so I was we were dealing with this hetero p-n junction, and this hetero p-n junction, you can see that it can help us to design the p-n junctions of our application specific purposes. So in here, when we are dealing with this silicon kind of a thing only, let's say for example, now it might have got charged. So for example, what I was saying, that I can have p material, for example, on the one side, which will be looking like this. EC will be like here, EC1, and this will be EV1, and I will be having n material, for example, it would be looking like this. So this is one kind of a heterostructure. Okay, so we can have likewise three types of heterostructures, but let's not get into that. I was telling about this because we were just out of but with what we can say battery. So now in this problem over here, you can see clearly that you are given this diode over here. This diode is basically a PN junction. It is now in forward bias, as it has been mentioned that this diode is in forward bias, and the DC current through it is 13 micro ampere. Now this you must have seen that this when going through the lectures, professor had solved for this resistance, this AC resistance of the diode. You must have gone through that. So junction capacitance of this thing is also given, thus of this PN junction diode is given to be equal to 1 nanofarad, and the angular frequency is 10 to the power 6 radians. So we have been told to find the magnitude of the small signal current that would be going through, or that would be passing through this circuit that is that has been shown over here, and this diode. So basically what we are being told to see, we have to find this what we can say this small signal. Wait a second. Okay, so we have to solve this for this small signal current through the diode. Basically what this diode will look like, this diode will be replaced by some resistance RD, let's say, and some capacitance. Okay, these are the two things that are associated with the diode, and rest of the circuit would look like as it was. Okay, this was 5 sine omega t kind of a thing, 5 sine omega t millivolts, and this thing was there was one resistor of 100 ohm, and this whole has been grounded. Okay, now for the AC resistance of the diode, you must have seen that this AC resistance of the diode is simply equal to, if I say this is the AC resistance, is equal to simply this RD is simply equal to thermal voltage by ID. You must have gone through this in the lectures. So this DC bias current is given to us, and this VT is simply 26 millivolts in this case, I guess. Yes, it's 26 millivolts, and this is 13 microamperes. So it is 26 into 10 raised to power minus 3, and it is 13 into 10 raised to power minus 6. So basically this RD would simply be equal to 2 kilo ohms. So this is the resistance that is associated with this PN junction diode. Okay, now for this small signal current that would be going through this what we can say this circuit or this diode, it would simply be this current, the magnitude of this current would simply be equal to this voltage that is being applied to it and divided by the impedances, simply using the Ohm's law, V equal to IR. Okay, this is the impedance for example of this, let me say this to be equal to Z1. This is minus J times XC, the reactance of the capacitance. So let us represent this whole thing with what we can say with Z1 and this thing with Z2. Okay, so Z1 is simply equal to RD parallel to the minus JXC, which is the reactance of this capacitance or impedance of this capacitance, and Z2 is simply equal to 100 ohm. Okay, so we know this capacitance, this reactance of the capacitance is given by 1 by omega C simply. So this XC is equal to 1 by omega. Omega is equal to 10 to the power of 6. So it is equal to 10 to the power of 6, and capacitance we have been given this value to be equal to 1 nanofarad. So it is 10 to the power of minus 9. So it is 10 to the power of minus 9, or this XC will come out to be equal to 10 to the power of 3. Simply it will come out to be equal to 10 to the power of 3. Now from this, if I look into this impedance Z1, Z1 is simply the parallel combination of this thing, which is this RD parallel minus XJ XC. So if I now do the parallel combination for this thing, it would simply be equal to Z1 is equal to minus J times XC plus multiplied by RD divided by RD minus J XC. Okay, so this is minus J XC. XC came out to be equal to 10 to the power of 3. So it is 10 to the power of 3. RD is 2 kilo ohms. So it is 2 into 10 to the power of 3. Okay, RD is 10 to the power of 3. Let me take 10 to the power of 3 as common. So it's 2 kilo ohm minus J times XC, where J is also, this is also J times 10 to the power of 3. So this is the impedance Z1 of this what we can say of this diode PN junction. This is its impedance simply. Now if I try to solve for this, clearly this will go with this. Okay, and we will be left with simply this J minus 2J. So now if I add this impedance, since this is in series, this impedance, these two are in series, Z1 and Z2, I would simply say this is Z1 plus Z2 is simply equal to minus J2 into 10 to the power of 3 divided by 2 minus J plus this resistance Z2 is equal to 100. Okay, it's equal to 100 ohms or 0.1 kilo ohms simply. So it is equal to 0.1 into 10 to the power of 3. Okay, simple. So it would be simply minus J into 2 plus 0.2 plus 0.2, wait a second, okay, plus 0.2 minus 0.1 J. This whole has been multiplied by 10 to the power of 3 and this divided by 2 minus J simply. So it would be simply equal to 0.2 minus, Krishna Paul, you can turn off your video, minus 2.1 J into 10 to the power of 3 divided by 2 minus J. Or let me write it clearly on the other slide because it is not showing up clearly over here, or let me write it down itself over here. It is 0.2 minus 2.1 J into 10 to the power of 3 divided by 2 minus j. Okay, so now we need to find its magnitude. Its magnitude would simply be equal to this is equal to 2 minus j, and it is simply equal to z1 plus z2. Its magnitude is equal to 10 to the power of 3. Let me take it to be equal to common. It was 0.2 whole squared plus 2.1 whole squared divided by, it was 2 minus j in the denominator, 2 square plus 1 square divided by this thing. So it is simply, let me calculate it. So it is simply 0.2 into 0.2, 0.2 into 0.2 is 0.04 plus 2.1 into 2.1, which is 4.45. We need to take its square root, 4.45. Good evening, Krishna Bhav. Okay, any question? 10 to the power of 3, 2.1095 divided by square root of 5. So it is square root of 5, which is 2.23. Okay, so it is simply 2.1095 divided by 2.23, which is 0.945, or it is 0.945 into 10 to the power of 3. So this is the magnitude of this impedance, which is in series. Now IAC, which is the magnitude of this current, was equal to this VAC divided by Z1 plus Z2 magnitude. Okay, VAC is having the magnitude of 5 millivolts. Okay, so it is 5 into 10 to the power of minus 3. Okay, and Z1 and Z2 are having the magnitude of 0.945 into 10 to the power of 3. So if I now divide this thing 5 by 0.945, it would come out to be equal to 5.3 into 10 raised to the power of minus 6 amperes, or simply 5.3 microamperes. So if we check for the options, there is one option, the first option, which is matching, yes, it's in microamperes. As you can see, it is in microamperes. So option A is the correct option to go with, and we have been able to get the correct answer for this. Now there is some quite interesting problem, that it says that we are having some charge profile which is shown like this in the figure 4. You can see, let me put the pencil on the charge till then. Okay, so it is shown in the figure where this concentration, you can see over here, it is clearly shown in the figure that this material is having PN junction kind of a thing, where the N side, where we are having both N side junctions, what you can say, we are having N on one side and N on another side as well. But the difference at this time is with the doping concentration. On one side, on the left hand side, the junction, on the left hand side of the junction, the material will have the concentration of the dopant atoms to be equal to 10 to the power of 16, while as on the right hand side of this junction, the concentration is simply equal to the 10 to the power of 50. Okay, now it means that there is concentration difference between the two sides. So as a result of this thing, we will be having this when we will draw our equilibrium Fermi level, it will be aligned, as a result of which there will be the transfer of the charge or the charge carrier. So when we see clearly this, when we try to what we can say, when we try to draw its energy band diagram, it simply means on the left hand side, what it means that on the left hand side I am having, since the material is of the same type, and on the left hand side I am having more dopant atoms. So if this is the EC1, this is the EFN1, okay, EFN1, and this is the EV1. And if this is the vacuum level, okay, this vacuum level will be constant throughout. This is the EC2. Since this material is little lightly doped as compared to the material on the left hand side, so it would be simply EFN2, which will be a bit farther than the EC2. Okay, this will be EV2. Both the materials will have the same band gap, everything is same, but only difference that we are having over here is the, what you can say, is the different doping levels. So as a result of this thing, we will be having clearly, or simply we will be having this when we draw its equilibrium band diagram, we will be having the Fermi level to be constant throughout. So the Fermi level will simply be constant throughout. As a result of this thing, EFN and EF2 will be simply merged, and we will be having a constant Fermi level EF, let us note it by EF. So as a result of this thing, this EC1 will be like this. It would be closer to the what we can say, this Fermi level in the bulk, and and since it was away in the case of the second material, so this was the EF for this second material, EC2. And now because of this what we can say charge difference, there will be the band bending, and this, it will look like this. If I consider this to be as the junction, this would mean that since this material one which is having a high concentration of the dopant atoms, it would try to there will be this transfer of electrons. It will try to transfer the electrons from the what we can say, from its levels, and as a result of which we will be having this electron transfer. This will result that this material will be having farther or more gap near the interface, because it has transferred more electrons, as a result of which the interface will be having less electrons as compared to the bulk of this material, because it has transferred the electrons at the interface. Similar is the case with this thing, although I have not drawn it to the scale. Let me draw it again. It would be like this, it would be like this, okay, it will be like this. This will be having more electrons as compared to the second material, M2 will be having more electrons as compared to the bulk of its what we can say, as compared to its bulk, because at the interface the transfer of electrons has occurred from the valence band, from the conduction band of this material 1 to the material 2, okay. So similar is the case with this valence band. It would also go like this. Please make sure these band bendings are same throughout, although in the picture it might look different, but they are same, okay. So this is the EV1 and this is the EV2. So now we have been told to find the built-in voltage. So built-in voltage is nothing but this difference, okay. This is what the built-in voltage is to us. So it simply means, if this is the built-in voltage, it is denoted by Q phi Bi. It is simply the difference between the two conduction bands, the conduction band 2 and that is EC2 and EC1, or simply EV2 minus EV1. This is the built-in potential simply that we will be having. But uh, let me ask you one question. If I am having, for example, this kind of doping, and D, which is constant in X, let's say, so what do you expect, or what do you say? Can you infer anything about this band bending? Can you infer anything about this band bending? How would it behave? What would be its function of X? Would it be a linear function in X? Would it be square function of X, considering this to be constant? This rho is constant in X, okay? This rho or ND over here. Will it be X cube? Will it be 1 by X or 1 by X square? Or what would be its function? How can you represent this in X? What would be the its physical form, that when you try to represent it in terms of X, or in terms of this position, what would it look like? So if anyone has answer to this question, he can unmute and try to elaborate on this a bit. Yes, anyone? Okay, since there is no answer, no. I'm not saying that doping is constant. Okay, this since this doping is constant, let us when we are solving for this, what we can say, this Poisson equation, you must have seen that this dE by dx is given by rho by epsilon. Okay, if this rho is constant and I am solving for electric field, it would be some function of x. Okay, electric field will be some function of x. Now I know this potential is minus times dv by dx. So this potential is simply function of x square. Okay, it is some function of x square. So this x square, as a result of this thing, if you see this band or bands are just minus qv, minus q times the potential. The band EC energy is simply the minus qv. Okay, energy is simply minus qv. As a result of this thing, if we try to relate this v with this electric field, and this electric field with the constant charge density, and this overall thing, when you equate it with the energy, it would be function of x square. So this thing over here for the constant doping, when I am having constant doping in the p junction and the n junction, for example, in here it is the n kind of material on both sides. When I am having constant doping, as a result of this, when these bands when these materials are joined, we shouldn't say joined, we say when they are brought in contact to each other, as a result of which there will be some band bending at the interface, and this band bending will be function of x, with x being the square power. Okay, so this x square, this the shape of these will be quadratic kind of a thing. Okay, so this will be quadratic kind of a thing for this pn junction. Let us keep these things in mind while solving for these actually. Okay, Vivek Chaudhary, yes, what have you said? Since doping is constant, will take place. Okay, Vivek. Okay, so it's fine then. So we were solving for this. Now I told you that this built-in potential will now simply be the difference between the conduction band edges. So it would simply, uh, please be careful of this thing. Whenever you are told to find anything regarding any new, what we can say, interface, just go for the Poisson equation. Okay, try to start from the basics itself. So now, if uh, this is the case that we need to find this built-in potential, which is simply the difference between the conduction band edges, I can simply write it down to be equal to Q phi bi is simply EC2 minus EC1, which is at bulk. Okay. Now, at a thermal equilibrium, we know that majority. Wait a second. Okay. Now, at thermal equilibrium, uh, we know that majority carrier concentration. Let us consider the first material, majority carrier concentration is simply ND1 is equal to NC exponential of EF minus EC1 by KT. Okay. Similarly, for the second material, it will be ND2 NC of exponential of EF minus EC2 by KT. Okay. So this is here, from here you can clearly see that I am having the difference in the conduction band and the Fermi level. Now we have to manipulate this expression in order to evaluate for the difference in the two conduction bands. For that we can simply say, we can simply divide this ND1 by ND2 by ND2 simply. So it would simply be ND1 by ND2 is equal to NC, and NC will go. It would be simply exponential of EF minus EC1 by KT, okay, divided by, sorry, exponential of EF minus EC2 by KT. Simply, or simply it would be exponential of EC2 minus EC1 by KT. Okay. So now this is the difference we were looking for. We were looking for this difference, this EC minus ET. So let us insert some slide and let us take the ln on both sides. It would mean ln of ND1 by ND2 is simply this EC minus EC2 minus EC1 by KT. Okay, so ln of ND1 by ND2, ND1 is to be equal to 10 to the power of 16 and ND2 is 10 to the power of 15. So it is 10 to the power of 16, it is 10 to the power of 15. This is multiplied by KT, KT is 26 millivolts. It is EC2 minus EC1. So it is ln of 10 times 0.026. Okay. So let us solve for this. Ln of 10 is simply equal to 2.303 into 0.026. So it comes out to be equal to approximately equal to 0.06 volts. Okay. So this is our phi bi. Okay, Q phi bi. So it is Okay, it shouldn't be q phi bi, it should be phi bi simply 0.06 volts. So let's check the options. Yes, so approximately it is 60 millivolts. 0.06 is 60 millivolts. So the option A is the correct option to go with. Okay, so this was about this problem where we had to find this built-in potential considering the same as the same material of n type but having different dopings. We said that the difference would simply be it would be simply the difference of in the conduction band edges. This built-in potential, we just took the pen and we draw this energy band diagram for this, and from the energy band diagram we said that it should look like this. Okay, now this problem over here, let me zoom it in a bit. Okay, zoom it in a bit. It says that this there is some charge profile of p-n junction. Okay, uh, and there is some intrinsic region. Okay, and such that this p let me close this down. Let me ask you people, where is this p what we can say, which side is doped with entire this dopant atoms and which side is doped with the acceptor atoms, or other words, which side will be p, which side will be n, and which side will be intrinsic. So I want you people to answer this. Please unmute one by one and try to answer this question. Which side would be p, which side would be n, and which would be intrinsic? Yes, anyone? Okay, I think there is no answer from you. So this since this ND is the, you can say this is ND minus NA, this profile, this y-axis is ND minus NA. So whenever it is positive, it means that there is doping. What I can say, we have used these dopant atoms to be used as the uh, external agents for enhancing the n-type concentration. And similarly, whenever we have used acceptor atoms, it would be, it would make this ND minus Na to be equal to negative kind of a thing, as a result of which we will be having peak which would be in the negative half of this graph. So this would be p type. So this would be p type kind of a thing. Okay, and this would be n type kind of a thing. Okay, and since this region over here it is having neither ND nor Na, so this will be intrinsic region. Simply it will be intrinsic region where we will be having no doping. ND is equal to Na. Simply ND equal to Na, or we haven't doped the material at all. So this is as simple as that. Now if we insert some slide and try to draw its energy band diagram again, let me clarify again. Whenever you have to deal with these p-n junctions etc, you you should draw energy band diagram first, in order to have insights about the what is happening at the interface. Always draw the energy band diagram. So the energy band diagram for us, it says that the material on the left hand side is what you can say, it is n type, or as a result of which we will be having, if I draw the energy band diagram in one go, I will be having this Fermi level which will be constant throughout. The material will be n type over here. okay, in the bulk, and the material will be P, okay, sorry, material will be P type on the right hand side, okay, in the bulk. So this is EV, this is EC, okay, and far away it would be looking like this. This will be EC on the P side, and this will be EV on the N side, okay. Now since the this material, what we can say, this has been uh, this has some intrinsic region in it as well. As a result of this thing, you must be aware now from this what we can say, from the Poisson's equation. You must know that how its slope will look like. It would be just the linear function in x in that region. So if it is looking like this, so if it's looking like this, so it would look like this in the intrinsic region, okay. So it would be at the junction, let's say it would be x equal to 0, and this would be, you can say this would be equal to this. If this is minus 0.5, yes, it was minus 0.5, I guess. Yes, it was minus 0.5. It is minus w, this thing. This is 0, this thing over here. This thing again is, I guess, 0.5. Yes, it is 0.5. This thing is w, okay, w. So this is 0.5 to w, this is minus 0.5 to 5, and this is the intrinsic region. Let me draw it like this. So this is the intrinsic region that we will be having, okay. Now we have to find the built-in voltage. Simply, built-in voltage is simply the difference in the conduction band. This conduction band, for example, if it is the P side, if it is the N side, let me write it down explicitly. So it would simply be, if I draw this, it would be simply the difference in the conduction band edges, okay. Now it would simply mean this built-in voltage again is equal to, it is equal to this ECP minus EC. So this is as simple as the previous problem that we had done. It simply means that this concentration on the, for example, on left hand side, which is ND, ND is simply NC exponential of EF minus EFN by KT. So this is for the N side, okay, this is for the N side. Similarly, for this P side, we will be having this NA to be equal to N, what we can say, NC. Let me write it in another way. Let me, since I have to look for the conduction band, I need to have the what we can say, in terms of the conduction band edge of the P side. So I will write it down to be equal to, since it would be this Na would be equal to Ni square. Since this Nd, for example, it would be looking like this. This Nd, this is the Nd1 on N side. So the Nd2 on the P side would simply be Ni square by Na. Simply, I have used the law of mass action, because we are in thermal equilibrium. So this N into P, the concentration of electrons into the concentration of holes, is simply equal to the square of the intrinsic carrier concentration. So it means this Nd2 is simply Ni square divided by Na, or simply it is equal to Nc exponential of EF minus ECP. So this, if this is ECN, this is ECP by KT. So this is for P side. So we have not done anything new here. We have just said, we have just used the law of mass action, and we have said this. We have just located, or we have just tried to represent this concentration ND2 in terms of the difference of the Fermi level and the conduction band edge on the P side. So let's add some slide again, and let's solve for this. Let us multiply this ND1 and ND2 simply. So it would simply mean, or let me divide these two things, because I will be having then this and this NC and NC will go then. Okay, so if I dividing, because I do not have any information about this NC, ND1 and ND2, I would be simply having this. This would simply be ND1 by ND2. ND2 is Ni square by Na. Ni square by Na. So it would be ND1 into Na is equal to Nc, and Nc will go, and we will be left with, let me write first, Nc exponential of, this would be Ef minus Ec of N by Kt divided by Nc exponential of Ef minus Efp by Kt. Okay, so this Nc and Nc will go, and we will be left with this exponential will simply be EFP minus, sorry, EF and EF will go, this EF and EF will go, it would be simply ECP minus ECN by KT. Okay, if now we take ln on both sides, this is ND1 into Na2 basically, this was Na2 basically, so this is Na2. Okay, so this ND1 into Na2 by Ni square, if I take ln on both sides, it would be simply, it would be simply Kt times ln of ND1 Na2 by Ni square is equal to ECP minus EC. So if I solve for this, it would be simply 0.026 ln of this ND is equal to 10 to the power 15, and Na is also equal to, wait a second, it is also equal to 10 to the power 15, this is also equal to 10 to the power 15, Ni is equal to 10 to the power of 10. Okay, so it would be simply equal to 10 to the power of 15 into 10 to the power of 15 divided by 10 to the power of 10 whole square, which is 10 to the power of 20, or simply this is equal to 0.026 ln of 10 to the power of 10. So ln of 10 to the power of 10, we need to find it out. So ln of 10 to the power of 10, wait a second, ln of 10 to the power of 10 is simply 23.02 into 0.026. It comes out to be equal to approximately 0.6 volts. So it comes out to be approximately equal to 0.6 volts. Now let's check the options for this. This built-in voltage, this option C seems to be the correct option, as we got this 0.6 volt. So the built-in voltage, we have been able to find this built-in voltage for this material which was having N type of doping on one side and P type of doping on other side, and there was some intrinsic region between the two. Now there is some other problem related with it. with the same problem that we were dealing with. This problem is the same for the same band diagram that we drew in this section or figure 4 for this question 5, sorry. So it says that in question 5, what is the value of 2 times the w? So we need to find this w. Okay, we need to find this value or w, and then we need to find its 2 times the w value. So basically we need to again go into the basics of this what we can say this Poisson equation. So if we go into the Poisson equation, then whenever this field, whenever we have this for example this doping on the right hand side and on doping on the left hand side, you must say that it would be some function. Since this doping is constant, it is some 10 to the power of 16 centimeter cube per centimeter cube. So whenever I integrated with respect to the electric field this constant value, it would give me this electric field to be equal to some function of x. Okay, it would be some function of x. Similarly, for this intrinsic region, okay, for intrinsic region, this dE by dx, since this intrinsic region is having no carrier concentration, so it is having this term epsilon naught to be equal to 0. As a result of this thing, the electric field will be constant in x. Okay, so this electric field is now constant in x. So if I draw this this electric field versus position for this material, it would simply mean that this material simply will have electric field profile looking like, which I will draw in this section. If this is the electric field axis, electric field, and this is the x-axis, okay, which is in some micrometers. Okay, now this electric field is constant because we saw this for this intrinsic region. Whenever we try to solve for the electric field, since this charge was 0 in this region, since this rho was now 0 in this region, yes, so the electric field will be constant in this region. So up to this, what we can say, up to this minus 0.5 to 0.5, the electric field will be constant. It will be simply constant up to minus 0.5 to 0.5. Then we are having some what we can say depletion regions on the N and P side, and we are having this charge at those doping concentrations, as a result of which we are having some rho associated with it, which is a constant in x, constant function of x. As a result of this, electric field will be some function in x. So it would be some linear function in x. Let me draw it like this. It is linear function in x. Okay, so this is minus w, this is plus w. Now this area under this curve will now give me the built-in voltage simply. So since this if I integrate this electric field, it would be this simply give me the built-in voltage. Now it means that this area under this this electric field, this is the maximum electric field. Okay, this is the maximum electric field. Area under this electric field, let me write it down explicitly. Electric field gives built-in voltage. Okay, built-in voltage. Now this built-in voltage is simply equal to area. So let me write it in terms of the area. Simply it would be the what we can say, the area of this area. Let us consider this half first. Let's consider this half first. Okay, and then let us consider this half, this triangle. So it would simply be equal to this area on this left hand side would simply be equal to E max. Okay, let me use the pencil itself. E max into 0.5, simply E max into 0.5 for this rectangle, and plus area of this small triangle, which would be simply 1/2 into this base. Its base is simply W minus 0.5, and its altitude is simply E max. Okay, this is the area of the left hand side. Since it is symmetric, oh sorry, let's not use this pencil. Since it is symmetric along minus x, the area on the left hand side would be simply equal to the area of the right hand side. So it would be, the total area would be simply 2 times this area of the left hand side that we found out. So uh, it means that we need to find this, what we can say, this maximum electric field simply. So let me simplify this a bit. It means that this is 2 times 0.5, which is 1 times E max, and this is also 0.5 times E max. So it is simply E max, this built-in voltage is simply E max plus W times E max minus 0.5 times E max, or simply it is equal to E max times 0.5 plus W. Now this is the simple condition on this, what we can say, on this phi bi. And now if we try to find out the what I can say, this maximum electric field, we need to use the Poisson equation again. So if I am using the Poisson equation again, and if I am trying to solve for the P side, we would simply, you must have seen this, that electric field is a function of Q times Na, where this x this W is the depletion width minus x divided by epsilon naught into epsilon r. This is simply, if I solve for the Poisson equation, and I will get this relation for the electric field, where the W will be the depletion width. Now I need to find the maximum electric field. Maximum electric field will be, let us say, at this point x equal to 0.5. It is also equal to x equal to 0, but since I know for this P side, I will be using this boundary condition of the P side of the material. So at x equal to 0.5 micrometer, simply this electric field is equal to E max. So this E max is simply equal to Q times Na, this W minus 0.5, which is in micrometers, epsilon naught into epsilon r. Now if I equate this equation 1 and equation 2, so let us say that using equation 1 and equation 2, using equation 1 and equation 2, this E max would, this phi bi would simply be equal to, this phi bi would simply be equal to Q times Na, epsilon naught by epsilon r, times this W minus 0.5, into this thing which came out to be equal to 0.5 into W. Okay, it is W plus 0.5, or simply this if I try to equate it, it is epsilon naught times epsilon r, it is phi bi, which is the built-in potential, divided by Q times Na, it is W square minus 0.5 square. Simply I have used A minus B into A plus B is equal to A square minus B square. Okay, we have used this relation. Okay, so it simply means this W square, okay, is equal to minus 0.25, and we need to find these values epsilon naught into epsilon r into phi bi. This epsilon naught, I think they must have given it. Since it is not given, let's take it to be equal to this epsilon r. Let's take it to be equal to the 11.7, which is for the silicon. So it is simply, this is simply equal to 8.85 into 10 raised per minus 14, which would be epsilon naught in centimeters, in which will be having in the units of farad per centimeters, and this will be 11.7, the uh, epsilon r, okay, and this phi bi, we found out it to be equal to, this is the phi bi, yes, let me check again, yes, this is the built-in voltage that we had found out to be equal to 0.6, this phi bi is 0.6, q is 1.6 into 10 raised power minus 19, and a is simply, equal to, Na is simply equal to 10 to the power of, wait a second, it is simply equal to 10 to the power of 15. Okay, so Na is simply equal to 10 to the power of 15. Basically, let us solve this. It is quite lengthy and I'm not able to solve this, but let us solve this. Okay, so it is 8.85 into 11.7 into 0.6, which is 62 point something, divided by 1.6, it's 38, 38.8, 38.82 into 10 to the power of minus 14, 14 plus 15, and it would be minus 19, it is 10 to the power of minus 10. Okay, it is uh, what you can say, in this came out to be in centimeter units, it is in centimeter square, while as this 0.25 was in micrometer, so it is micrometer square. Okay, so this is W square minus 0.25 micrometer squares. Okay, so it means 0.25 into micrometer is 10 to the power minus 6, it is 10 to the power of minus 12 meter squares. Okay, now let's add some slide again. So I have to convert this meter into a centimeter, so it will be simply 10 to the power of minus 2 centimeter square. Sorry, since this is micrometer, let us keep it in micrometer. Let's convert the other thing, this centimeter thing, into the, what you can say, meter. So this 38.82 would be simply now equal to 38, because we need to find it in the micrometers itself. 38.2 into 10 to the power of minus 10 centimeter square into 10 to the power of minus 4 meter, so it would be 10 to the power of minus 14 meter square, plus it is 0.025 into 10 raised power minus 12 meter square, or 25 into 10 raised power minus 14 meter square. It is 25 into 10 raised power minus 14 meter square. This is the value of this W square. Okay, so if we add these two, it is simply 38.2 plus 25, which is root of 63.2, it is 7.95 7.95 into 10 to the power of minus 0.7 meter. This is the value of W, or simply it is equal to 0.795 micrometer. This is the width of this depletion. This is the depletion width. So this is the value of W, but we were required to find the value of 2W in micrometer. So we have to multiply this thing with 2 times. 2W is simply equal to 2W is simply equal to this thing. It is 15.9. It is 15.9 micrometer. Okay. So let me find out which is okay. It is option C, which is matching our results. So we would go with this option C. This option D. Sorry, this option D is matching our results. So it is 15.9 approximately. As a result of this thing, we will be getting this to be equal to W equal to 15.96. Now the same problem, it is related to the same problem. It says that is in this question 5, what is the value of the electric field at x equal to 0? Okay, so x equal to 0 means the electric field which is the maximum electric field. So simply this we had found out the expression for the electric field previously, and it was this expression. Where is it? Yes, this expression phi bi is equal to E max times 0.5 plus W in micrometers. Okay, so it would simply mean this phi bi is equal to E max times W plus 0.5. So E max is simply, W came out to be equal to 0.795. 0.795, it is in micrometer. Let's be careful about this thing. Plus 0.5, it is in micrometer, which means 10 to the power of minus 6. Okay, phi bi is 0.6. Okay, so it is simply 0.6 divided by 0.5 plus 0.795. So let me add this up. 0.5 plus 0.795 is 1.295. 0.6 divided by 1.295, it is approximately equal to what I can say 0.46. 0.46 2 into 10 raised power of 6 is the electric field, E max, volt per meter. Okay, volt per meter. This was in micrometer, now it is in volt per meter. So it is simply equal to 4.62 into 10 to the power of 5 volt per meter. This is the value of the maximum electric field. So option C seems to be the correct option for this, and we will be selecting this option C for this maximum electric field. Now we have some quite interesting problem about this PN junction again, which says that this PN junction, this is this PN junction, this style is abrupt PN junction, that we know we are using this abrupt PN junctions every time, that on P side to N side everything goes in a jiffy. What we can say, there is no, we can say this P to N transition. Whenever we show the doping, we just show it by the constant lines, what we can say constant lines, and then it changes from the P to N within a jiffy. So this abrupt junction has been chosen, as a result of which this this material is doped such that the acceptor concentration is equal to 10 to the power of 18. Okay, and this donor concentration is equal to 10 to the power of 15. So from looking at this, it would mean that this whenever we solve the Poisson equation, you must have seen this NdXn is equal to this NdXn is equal to Na xp. Okay, so it means that if this is high, this will be low. Simply it would mean that this is low, then this is high. Okay, you must have seen this while solving for this p-n junction. So this relation is also handy sometimes, but let's not get into this. But uh, the point here was to tell you that if this Na is highly doped, so it would mean this Na is highly doped. It would mean that the depletion width on the uh, p side would be less. Okay, on the p side of this p-n junction. So the main thing was, the main idea was to get that thing only. Now this uh, it has been told this p injection has some area which is 6 into 10 to the power of 4, and this now we have placed some inductance. Some inductance has been placed in parallel with this p-n junction. As a result of uh, this thing, it means that there will be, since we know this, the p-n junction will have some capacitance associated with it. Now since we are using some external conductance in terms of this inductor, we are using this inductor and keeping it in parallel with this p-n junction. So there will be this LC kind of a circuit that we will be getting. As a result of this thing, uh, uh, we will be getting this LC oscillations kind of a thing, and we will be having this resonant frequency. You must have seen it. This for this LC circuit, this resonant frequency of parallel LC circuit is simply given by f naught equal to 1 by 2 pi root of LC. Okay, so what we are supposed to find over here is the value of this capacitance first, because we know this value of C, this 2 pi is constant, so we need to find the value of this capacitance that is associated with this p-n junction. So the capacitance can be simply found by this, simply this capacitance is equal to simply epsilon naught into epsilon r into area divided by the depletion width, or the region of this, what we can say. So this WD is simply given by 2 times epsilon naught into epsilon r into VBI plus what we can say, VBI. Okay, this VR is given to us, yes, so that's why we can easily take this to be equal to the depletion capacitance. I thought that we might have to take the diffusion capacitance as well, but since it has been told that the p-n junction is in reverse bias, so this depletion capacitance will be there only. So it would be VBI plus VR into 1 by Na plus Nd. Okay, it would simply mean this, for this particular case we need to first find out VBI, which is simply Kt by Q ln of NaNd by Ni squared. Okay, which is 0.026 ln of 10 to the power of 18, and it was, I guess, 10 to the power of 15. Yes, it is 10 to the power of 15 by Ni. Let us check the value of Ni. Ni is 1.5 into 10 to the power of 10. So it is 1.5 into 10 to the power of 10 whole square. So this is the this value we need to find out. It is 10 to the power of 18, 10 to the power of 15, which simply means that it is 10 to the power of 33, and this has to be divided by 10 to the power of 20, or simply 2.25, 10 divided by 2.25, it is 4.44. Okay, it is ln of 4.44 into 10 to the power of 10. Okay, 10 to the power of 10 into 0.026. So it is 0.63. So let me again calculate it. I guess I might have missed some value. So it is 2.25, 10 divided by 2. Okay, 2.25, it's 4.44 ln of, it is simply ln of 4.44 into 10 to the power of 10 to the power of 12 into 0.026. So it came out to be equal to 0.757 or 0.76 volts approximately. This is the value of VBI. Now if I now put the value of this VBI back in this WD, I would simply get this. Let me just put the values and you people solve it by yourself. So it is epsilon naught into 8.85 into 10 to the power of minus 14 into epsilon r is 11.7, VBI is 0.76, and VR is reverse bias voltage is 1 volt. Okay, it is 1 volt. So it is 1 volt divided by 1.6 into 10 raised to power minus 19. Okay, 1 by NA. NA is simply 10 to the power of 18. So it is simply 10 to the power of 18 plus 1 by 10 to the power of 15. From this, you will get the value of this, what I can say, depletion rate, this WD, and from that you can find this capacitance simply by equating it to be equal to epsilon naught R by epsilon R A by WD, and from that you can simply equate it to be equal to 1 by 2 pi root of LC. L is equal to 2 point, I guess, where is it, 2.2 millihenry. It is 2.2 into 10 raised to power minus 3 times this capacitance. So from this you will get the value of this what we can say resonant frequency. I am not trying to solve for this thing because it is just this cumbersome calculations and it takes just time to solve for these calculations. Okay, now if we now solve for this another problem that we are having. Okay, I have solved this. Now there is some another problem. It says that this PN junction, we have to consider an ideal PN junction diode which is at 300 Kelvin, uh, and the current through this PN junction diode is simply 2 milliamperes at when the forward bias is 0.1 volt. We need to find its reverse saturation current. So simply you must have seen the current for this ideal PN junction diode is simply given by I naught, where this I naught is reverse saturation current, I naught times exponential of VA, VA by VTH minus 1. Okay, VA is the applied bias. Okay, applied bias. Fine. Okay, so it means that the current is 2 milliamperes, and we need to find out this I naught, given that VA is equal to 0.1 and VTH is simply equal to 0.026. point, oh sorry, not 0.26, 0.026, 0.026 minus 1. Okay, so if I divide this by 0.1 divided by 0.026, it is 3.846, 3.846. Exponential of 3.846 is 46. If I subtract 1 from it, it will be 45, simply 45.8. 45.8, it is equal to I naught times 45.8. So if I now divide this by 2 divided by 45.8, it would be approximately 40.0437 into 10 raised power of minus 3 amperes. Okay, this milliampere I have converted into 10 raised power minus 3. This is the reverse saturation current, or simply it would be 43.7. 43.7 micro amperes is the reverse saturation. Okay, so the option A seems to be the correct option for this, as a result of which we will be selecting the option A. Okay, now let's move towards another problem, which says that we have this ideal PN junction which is forward biased, and as a result of which this is actually, it is moderately forward biased, such that the applied bias is greater than the thermal voltage. Okay, so it means that, let us again, it is showing goes like this. Okay, solution for this is simply this VA is much greater than VTH. Okay, so it simply means that this equation of this ideal diode current is simply approximately equal to I naught times exponential of VA by VTH. Since this VA is much greater than VTH, we can neglect that minus 1 in this. So it has been told to find that how much voltage is needed to increase the diode current by a factor of 10 at 300 Kelvin. So the temperature is 300 Kelvin itself. Now this, let us say this delta VA is the some additional voltage, that is there is some additional voltage required to increase the current by 10 times. Okay, so this current now is 10 times I, and it is equal to I naught exponential of VA plus delta VA by VTH. So it is simply equal to I naught exponential of VA by VTH into exponential of delta VA by VTH. Okay, but this I naught times VA times VTH is simply this I, so this 10 times I is simply equal to I exponential of delta VA by VTH. So it simply translates to 10, this 10 is equal to exponential of delta VA by VTH. So this ln of 10 times VTH is the change in the applied bias that is required to change the what we can say, change the current magnitude by 1 decade. Okay, so if I now what I can say, solve for this ln of 10 into what I can say 0.026, so it comes out to be equal to 60 millivolts. Okay, so let us remember this thing, not let us just keep this thing in mind, that whenever we are required to find the 1 decade change in current for a diode in what you can say forward bias, it is required to have the applied bias voltage change of approximately 60 millivolts. So it means that if I want to change the current in the PN junction by, for example, 10 to 100, it would mean that I have to increase the bias by the 60 millivolts or 0.06 volts. So this is valid in forward bias, and this is valid at room temperature. Okay, now let's move towards some problems of this bipolar junction transistors, and let us just get started with this BJT itself, and let's try to see how much we can solve in this lecture itself. So it says that these parameters of the base region are given to us, and it is given by this dn equal to 20 centimeter square per second, which is a diffusion constant of the, or what we can say, of the electrons in the base, which means this means that this base will be having electrons as the minority carriers, since this is an NPN BJT. Okay, this is an NPN BJT. So basically, what you can consider this BJT, you can consider a BJT as two PN junctions in series. Okay, or you can consider them to be connected together. One is NP junction and another is the PN junction, just for the sake of understanding, just for the sake of illustration. Okay, so it means that we now have to basically in this problem, let us see what other parameters we have been given. First, we have been given this NB naught, we have been given this area of this ABE, we have been given this width as well for this base, and we have been told to find the collector current value when this base emitter voltage, which is the VBE, is equal to, okay, somebody needs to join. Okay, when this base emitter voltage is equal to the 0.6 volts. So this collector, and we have to find this value when the collector base junction is reverse bias, and we have to assume that this thermal voltage is equal to 26 millivolts, which is the always the approximation that we take. Now if we solve for this, you must have seen this collector current is simply let me myself check this first. Okay, collector current. So collector current is simply equal to Q times area Ni square, Dn is the diffusion of constant of these electrons, times XAB times the NAB. Simple. But this I can write this Ni square by NAB simply to be equal to the minority carrier concentration in the base. So this minority carrier concentration NB naught, I have been given this value, which is 10 to the power of 4. It is basically 10 to the power of 4. Okay, so this NB naught is equal to Ni square by NAB. Oh, sorry, I forgot to write this complete equation. Exponential of Q times VBE is the base to emitter voltage, KT minus 1. So this Ni square by NAB is the minority carrier concentration in base. Let me write it down explicitly. Minority carrier concentration in base. Okay, so we know this value, we know this x of, sorry, this shouldn't be x of AB, this should be 6, simply x of base. So this is x of base simply. Okay, x of base is the base width simply. So if I now solve for this collector current, it is simply equal to Q times ABE, and let me first write down all the values that we need. So this ABE is 10 to the power of minus 4 centimeter square. Okay, this NB naught is equal to 10 to the power of 4 per centimeter cube. Cube we know, area is given to us, and dn is equal to 20 centimeter square per second. Okay, base width is given, and this base emitter voltage is given to be equal to 0.6 volts. Okay, and this now from this this VTH is also given. VTH is 26 millivolts, and this XB, X of base, is given to be equal to 1 micron. So it is 10 raised power minus 6 meter. Okay, simply 1 micrometer is 1 micron is 10 to the power of minus 6 meters. Okay, so now if we put the values, so I naught would simply be, equal to 1.6 into 10 to the power of minus 19 times the area is 10 to the power of minus 4 times the this NB naught is 10 to the power of 4, 10 to the power of 4. This dn is simply 20 into 20 divided by this xb is the 1 micrometer or 10 to the power of minus 4 centimeter. Okay, into exponential of VBE. VBE was, I guess it was 6.6. Yes, it is 600 millivolts and it is 26 millivolts. So it is exponential of 600 millivolts divided by 26 millivolts minus 1. Okay, so let us solve for this and let us see how much we will fare for this. Okay, so it is exponential of 600 by 26, which is 23.07. so it is exponential of 23.07, sorry, 07. Oh, it is quite large number. It will take time to solve this. Let me do it like this. Let me cancel this. It is 1.6 into 2 into 10 to the power of 5. It is 10 to the power of minus 14. Okay, it is 10 to the power of minus 14, I guess. Yes, 5 5 minus 80 minus 14, and it is 1.6 into 2 3.2. This value is equal to 1.045 into 10 to the power of 1 2 3 4 5 6 7 8 9 10 into 10 to the power of 10, or simply I can say it is equal to 3.2 into 1.045, which is 3.34. It is equal to 3.344 into 10 to the power of minus 4 amperes, or simply it is equal to what I can say 0.3344 milliampere. This is the value of this collector current IC or I naught, whatever we can say, 0.33. So it is equal to option B is matching with our options. So we will select this option B. So I think that's it for today's session. So if you have any questions or any thing that I want to repeat in the today's lecture, you can ask me, or otherwise we can end the session in 5 6 minutes. So please ask the questions if you have any question, or if you want me to repeat anything, we can go again through that problem if we have any question. Yes.
So can you explain the first problem again?
Okay. First problem. Okay. Yes. So here is it. What we have basically done over here in this problem, we have simply used this diode model. We have simply replaced this diode. We know that this PN junction will have some resistance associated with it. That is one thing. And the second thing is we will be having the capacitance associated with this PN junction as well. Now in this problem there is one twist. We have been told to use this PN junction. We have been told to put it in some circuit, and this circuit is given some or can say sinusoidal signal. Okay, this sinusoidal signal, it, okay,
So there is another voltage we know.
where, okay,
Yeah.
this is just for the DC biasing. Okay, this is for the DC biasing.
So it
Oh,
doesn't have any significance.
no, no, it has significance. It is forward biasing the diode. Okay,
Okay, sir. Thank you, sir.
okay. So this is the main significance of that DC bias. Yes, absolutely.
Okay, sir. Thank you.
So this whenever we bias this diode now, as it's given in the problem as itself, this diode is forward biased. So the DC current through this is some 13 microampere. And now we know this. We can find this RD value, which is this what I can say this uh, the a dynamic AC resistance, which is associated with this PN junction diode, and we can find this capacitance which is associated with this capacitive reactance which is associated with this PN junction. So that's what we do. We try to find this impedance Z1, and since this Z2 is given, we say that this a current through this whole circuitry will be simply, the magnitude of this current will simply be given by the VAC divided by the impedance that we are having, the total impedance, which is Z1 plus Z2. Z1 is simply the parallel combination of two impedances. One is the RD, which is the AC dynamic resistance, and another is the reactance due to the capacitance. So this capacitance is we have been given this capacitance value to be equal to 1 nanofarad. Okay, and the operating frequency is also given to us, which is 10 to the power of 6 radians. As a result of this thing, we try to find out the parallel combination impedance, and we get this value to be equal to some j times minus j times 2 into 10 to the power of 3 divided by 2 minus j. Now since we are interested in the magnitude of the impedances, we just take the series combination of these two impedances Z1 and Z2 and simply take its magnitude. And when we find its magnitude, we simply say that this AC voltage source will be having some magnitude which is 5, I guess 5 millivolts. Yes, so we divide this magnitude of this AC signal by simply the magnitude of the resistances or the impedances that we are obtaining. Okay.
Thank you, sir.
Okay, let me ask you people one question about this. For example, mm, if I am having some charge in till now we have seen that this charge is constant, for example, I have, sorry, this concentration density, or which at the end boils down to charge also. So if I am taking this Nd, for example, this doping concentration of the dopant atoms to be equal to constant, and some value equal to, for example, I take it to be equal to 10 to the power of 16, for example. But let's say that if this concentration, for example, is 10 to the power of 16 times the function of x, for example, where x is the distance from the, what we can say, interface. So this would mean that this charge, or the concentration that we are looking over here, this concentration, this has some, what we can say, although it might not be physical, what I am saying, because it would mean that the doping concentration is increasing linearly with x, but let's try to limit it with, for example, between the limits of minus, for example, minus a to plus a. So it means that if the doping concentration is a function of x, so what would you say about the electric field? What would it look like? Just by solving the Poisson equation, what do you suggest its shape should be? So anyone, uh, can answer this. So what do you feel about the shape of this electric field? Yes, anyone. Let it be wrong. Let me give you one hint. It should be solved using the Poisson's equation. I'm telling you that this concentration is a function of x, linear function of x. So it means that since every time whenever I am giving you the charge, or this, what you can say, this doping concentration, or you can say uh, uh, the electronic concentration, you should go for the Poisson equation. Whenever I am dealing with these kind of things, the first thing that should come to my mind is the Poisson equation. So simply over here, I should also consider the Poisson equation. So I should go back and say that I will go to the Poisson equation and say that for 1D case, this derivative of the electric field will simply be equal to rho by epsilon. If this rho is now the function of a linear function of x, that is the distance, let us say, so it would mean that when I integrate this thing with respect to the when I integrate this thing with respect to the dx, it would mean the electric field will be some function of x square. So that's what I was trying to say you when we were just drawing those PN junctions, how the electric field at the interface would be a function of x. Would it be x, x square, would it be constant? So for that I had told you to find the electric field, and you knew that the electric field will be constant in that case because the concentration was constant, as a result of which field came out to be equal to f, as a linear function of x, and as a result of this thing the potential or the energy band bending came out to be as a quadratic function of x. Okay, so you should try to get some insights into this whenever you are being told to solve for these kind of things, like as I told, I am giving you the charge concentration or something like that, the electron concentration, the hole concentration, or some doping like that thing. You should try to solve it with the Poisson's equation. And one more thing that I would like you people to do is that whenever you have some interface problem, just go to the band diagram, draw the band diagram, make the constant, make the Fermi level constant, do the charge transfer, whatever the carrier transfer is occurring, and see from you will get insights that how that this simple band diagram, whenever I draw this simple band diagram, how much insights I can get about this physical system or about this interface, and I will be able to solve each and every problem regarding the device physics of the particular material or that particular device that you are studying. So if we have no questions, I feel that we can end this session of ours today. So we hope that let's meet on the next session. So I request to people, if you have no question, to leave this session. Otherwise, if you have some question, we can discuss that question again, because we have time. I think 5 to 10 minutes. So if you okay, thank you, Akshay. So if we have no question, we can leave one by one. So let me end this session. Remove. Okay.